Yeah, good morning. In this session, I would like to demonstrate simulation of some simple blocks like mixer, flow splitter, and component separator by taking a few simple examples. So let us go ahead with simulating these examples or these models in Aspen. So for the time being, let me consider some components to demonstrate the use of these models. Say for example, benzene and toluene. Of course, there is no limitation that we need to use only two components. Just for demonstration purpose, I am using a binary mixture. So go to the next input step. Usually in any process simulation, this is the first step. You need to define all the components that you are going to handle in your process. So after completing this first step, the second step is to choose an appropriate property method. In fact, you can go through this methods assistant, which will, by answering a few questions, you will be able to narrow down the choice of property methods to a few. You may be able to use one of them. Anyway, these are simple examples, so let me assume some property method, Chavo Cedar. So this is the second step. Then go to the next step, wherein you are required to go to the simulation environment. Remember, when you normally open Aspen, by default, it will try to perform the property analysis. So if you want to go to other aspects like simulation, you need to click on this and say OK. So this is the third step. Then the fourth step is using some of the models already available, develop the flow sheet using this graphical user interface. So as I said, I'm going to demonstrate a simple unit like mixer. Now, once you select this mixer, then I need to add material streams. Now, with little practice, you should be able to draw these flow sheets quite easily. As you go nearer to this red, please observe this is feed required, this is product required, and all the connectivities cannot be answered. This is only this is optional. In case if you want to have water decant, then only you need to live to this. But these two are mandatory. So as you go nearer to this port, you can see the color change. So hold your leftmost button, drag it, because you are going to disturb the position, drag it wherever you want. Drag your mouse and click leftmost button. So automatically it is connected. Similarly, I'll also add one more input stream. You can see the color change. Keep your leftmost button clicked and then drag it. Once again, you will be able to add another stream. By default, it names it as 1 and 2 or S1 and S2. Typically, in any process simulation, we will be considering flow of material between two units as a stream. Of course, this stream 1 is going into a mixer, but where from it is coming? You know. So you can consider this as some kind of a storage tank from which you are drawing this material. So you can consider stream 1 is connecting storage tank with a mixer. Similarly, let me also add one output. So this is the output stream. Again, as you know, material cannot be destroyed. That means this material is going into maybe a storage tank. Now, if you want, you can name these streams. You can name the block. So if you want, you can try those. Now, once you draw this flow sheet, you can go into the next input step by pressing N. Remember, this model is going to work in rating mode. You know, for a rating problem, things must be specified and along with operating conditions and equipment parameters. The operating conditions and equipment parameters are likely to change from one unit to another unit. So accordingly, you need to address. Given this information, you will be calculating the output. Remember, whenever you are trying to use a rating model, you will never be in a position to enter information with respect to the output stream. For example, if I expand this, you can see the red dots on the left-hand side menu need to be addressed in order to complete the problem definition. So it is asking information for stream 1 and stream 2, but no information is being sought with respect to the output because it is going to calculate the values of the output stream. For example, if you forcibly open this and it provides some input, that would be ignored while solving this problem, right? So let me go to the next input step by pressing N. The advantage by using this N is, in case if you are not complete in providing the required information in a tab, it will not allow you to go to the next tab. So this will always be preferable. Instead of jumping from one level to another level, unless you are experienced, always use this next button. Okay. Now what is that we are supposed to address? We are asked to provide information with respect to stream 1. We already saw the degrees of freedom for specifying a stream is 2. Now we have two components. If both the components are involved in the stream, we need to define at least 4 variables. So C plus 2, the two variables must be either temperature, pressure or vapor fraction. Out of the 3, liberty to choose any 2 of them. For example, let me take different possibilities. For one stream, I will be addressing temperature and vapor fraction. So temperature, let us say I am assuming some 25. Vapor fraction is 0. That means it will be calculating the pressure for the given composition, considering that that particular stream is a saturated liquid. So from the phase rule, you will be able to establish that the system will be able to exist as a saturated liquid at this given temperature, only at a given pressure. So we will be able to calculate the pressure. So let me consider there are 2 options. When you are talking about C plus 2 variables, plus 2 variables must be any 2 from temperature, vapor fraction or pressure. What about the remaining C variables? This is based on Gibbs-Duhem equation, which says we should be able to know the initial masses of each and every component, mass, moles or volume. So for example, let me consider 100 moles of benzene, 100 kilomoles per hour of benzene is entering, 100 kilomoles per hour is entering. Right? So you can see now, because we were able to define 4 variables, the degrees of freedom is satisfied, then the required input for stream 1 has turned from red to blue. Right? Minimum information required for defining the stream is addressed. Now we need to address stream 2. You can say next. There is another option. Instead of defining the individual component flow rates, I can say the total flow rate of this stream 1 is 200. Then probably I can define mole fraction as 0.5 because both are equimolar and 0.5. You may presume that we have defined 5 variables, but remember, in a binary mixture, once we know the mole fraction of one component, the mole fraction of the second component is not independent. However, because you are trying to describe all the components involved in the problem initially, so this will be having the list of components that you have already defined. It doesn't mean that all these components are going to be present in each and every stream. So it is always advisable, if you are defining the total flow and mole fractions, though it is not independent, try to define such that the sum of mole fractions is equal to 1. Otherwise, it will be difficult for the simulator to identify whether you are using, out of the available components, how many components are available in this stream. So please make this as a good habit. Or if you are not conversant with this, 200 multiplied by 0.5 will represent the benzene flow rate. So define the flow rate of benzene as 100, toluene as 100. You need not have to talk about this total flow rate. Either way, it is the same. Either way, you are addressing the total initial masses of each and every component. Okay, let me go to the next input step. Similarly, for some reason, let me address 25 and vapor fraction. Earlier I have said 0. Now I would like to put 1 for the same composition. Right? Of course, you are at liberty to give this data as per your requirement. Now you can see the required input is complete. In the case of mixer, you don't need to provide any operating conditions or equipment parameters. Normally, where do you come across this kind of an operation in our practice? We know 2 input streams, especially fresh feed, will be mixed with the recycled feed to provide the combined feed that usually. So 2 input streams, feed and recycle, are getting mixed to give rise to the output product. Okay. So because we have completed the required information, then press next, run the simulation. Now you were able to solve this model and with no warnings and errors. So the results you must be in a position to see. There are three different ways of looking at your results. The first thing is you can click on this stream summary. Now you can see all the required information with respect to all the streams involved in your flow sheet in this report. So what is the temperature? These temperatures are given, the vapor fractions are given. So it calculated the saturated pressure at which it is going to be in saturated liquid form at this pressure. So this is, in other words, bubble pressure, and this pressure. Now the question here is, how do you think it calculated the outlet pressure? So in the case of a mixer, the outlet pressure is minimum of the two inlet pressures. So automatically it puts this value. Now the question is, how do you think the outlet temperature is calculated? Now this is a typical problem. By performing mass and energy balances, we will be able to establish, for example, 200 moles each of stream 1 and stream 2 are entering. There is no chemical reaction, so the total moles leaving the process is 400. Now these are component balances, benzene 100 through stream 1, 100 through stream 2. So together they should exit 200. So from this we will be in a position to calculate, of course these are given, but we will be able to calculate the composition of the exit stream. So in the same way, we will also be able to identify the mass flow. Though we gave the mole flow rate, how do you think this mass flow rate is calculated? We may need density, which is calculated here. So using the density, it will be converting the molar flow rate into mass flow rate. And you know, there is no, the mass flow rate, both are equal because the compositions are equal. This is the total mass. And these are the moles, mass of each component. Similarly, if you are interested, you can also see mass fractions. All of them will be uniform, right? So this is the information that it will be providing. And similarly, if you try to look at the enthalpy, the total enthalpy entering through each of these streams, right? Okay, not this is calories per gram, calories per second or something like that. Let me see this one, right? So this is the amount of total enthalpy, molar enthalpy multiplied by the molar flow rate. So of course, in terms of calories per second, this is the enthalpy entering, this is the enthalpy leaving, and this is the enthalpy through stream 2. The sum of these two should be equal to this, right? So we know the pressure of the exit stream, the composition of the exit stream, we know the enthalpy. Now, how do you think you will be able to calculate the temperature? Please think about this question, whether you are in a position to calculate this temperature or not. In fact, in the simulator, it will be performing an adiabatic flash. That's how this temperature is estimated. You can probably verify this calculation if you are able to do by manual calculations. Now, in this case, we were able to represent certain properties which may be needed to perform mass balance, enthalpy, energy balance, maybe entropy balance, and so on. The required information in the standard form is going to be present in its report. But for some reason, if you want to add any properties and also list out those properties here, you should be in a position to do that. I think in one of the exercises, I have already shown you this. So this is how you will be in a position to simulate a mixer. It doesn't mean that you need to use only two components or only two streams. Suppose any number of input streams can be mixed to give rise to one output stream. So it is possible to add any number of inputs, but there is only one output stream that is possible here. Okay. Now coming to the second model, splitter. Let me go with the new simulation. Two components, right? So I have been defined the components, choose a property model, simulation environment, create the flow sheet. Now this is where the splitter model is available. Now this is the reverse of the mixer. In the case of a mixer, two or more input streams are mixed to give rise to one output stream. Whereas in the case of a splitter, one input stream is getting divided into two or more output streams. Again, you can draw any number of output streams based on your requirement. Now, where do you normally come across this type of stream splitting? Typically, before we send the unconverted gases into recycle, in case an inert material present, we would like to take out a small portion in the form of a purge and the remaining is recycled. Or you consider the condenser in the case of a distillation column. The exit from the condenser, part of that is withdrawn as a remaining part is sent as reflux. So you can identify such applications. But this is probably one of the most simplified blocks that you can presume. The chemical and physical state of all the three things will be similar. The temperature, pressure, the composition will not be affected. It is only going to divide the flow either in terms of mass, volume or moles into two parts according to the desired split fraction. If I want, I will be able to divide 50% of this into S2. Automatically the remaining 50% goes into S3. Or I can take 5% of this S1 in stream 2, the remaining 95% goes into stream 3 without affecting the chemical state and physical state of the stream. Now anyway, let us go into the details. Once again, you can see that we are asked to represent information S1, this being the input stream, and of course some information with respect to the blocks, but nothing with respect to S2 output streams. Again, this doesn't matter. I am presuming certain values. Like what I did earlier, I will be using the same. Or you can do whatever you want as per your requirement. So we have defined stream 1. So go to the next. Now we are being asked to provide information with respect to this block. Earlier in the case of a mixer, we did not have this. Now remember the outputs are S2 and S3. Now from the given input, how much value, how much flow should go into S2? For example, if I say something like 0.2, 20% of whatever is entering into this splitter through S1 is routed through S2. What will happen to the remaining 80%? Because you know, nor created nor destroyed, so the remaining 80% automatically goes into stream 3. Suppose if I have 3 output streams, I need to define at least 2 split fractions so that the total mass is divided into 3 outputs. So if there are S output streams, at least S minus 1 split fractions must be defined. In this case, because there are 2 outputs, 2 minus 1, at least 1 value must be defined. In fact, you can also change this basis into, you can say flow and decide out of the 100 moles that is entering, it may be sometimes necessary to maintain a minimum amount of flow in case if S1 is changing due to some other operations in the process. You can also specify this way. But if you are trying to specify this way, you have to make sure at least this much of flow is entering into the splitter through S1. So this is another possibility. Let me revert back to split fraction. Revert to 0.2. Right? So you can see the required input is complete. Then go to next. Again, you can, sorry, I did not show you the other ways of looking at this. You can go to stream summary. Now you can see the temperature and pressure of all the 3 streams is unique. Remember, we have defined only the input stream, and similarly, the compositions also will be exactly similar because we are only trying to divide the flow according to the given split fraction. What did we say? 20% of whatever is entering should be routed to S2. The remaining 160 kilomoles should go into S3. So whatever is the fraction, you will be able to achieve this by using a splitter, right? Again, you can observe what are the typical properties that are normally listed in this stream summary. This is one way of dealing with looking at the results of any process simulation. And the other way is you can click on this report. You choose whatever you want, block, streams. So all the streams are only one stream, you choose accordingly. So the report will be generated in a notepad format which can be saved and printed or kept for some reference for further use. It's up to you. Now you can see automatically what is S1, where from it is coming, maybe a storage tank, it is not a unit, it is entering into B1. S2 and S3 are the outputs, so they are coming from B1 going to maybe storage tanks. So all this information based on the flow sheet, the simulator will be developing. Whatever you are able to see earlier in the stream summary, all the details are now available stream wise in this report. This is another way of looking at your results. The other possibility is you can go to the main flow sheet. Now click on any stream, right click, look at the results. So the results of that stream can be viewed. And similarly, you can also see the results of this block. When I say simply click on the block and say results, normally these are the calculations that are made for each and every block. The model will perform the mole balance, what is the number of moles, total number of moles entering into the system, entering into the block, number of moles leaving. Because there is no chemical reaction, mole balance is satisfied. Similarly, mass balance is satisfied. Similarly, enthalpy balance is satisfied. So when you have more number of units in your flow sheet, this kind of calculations are done for each block as well as the entire flow sheet. This is another way of looking at the results. The other possibility is click on this and say stream results. Whatever are the inputs and outputs connected to this block, all the streams are automatically represented in these results. Right? You can see S1, S2, S3, all of them are represented here. So based on your convenience, you should be in a position to take these reports in whatever form you want. For example, if you try to click here on this, you will be able to copy all this information, which can be pasted either in Word, Excel, in whatever way you want. Right? This is how you will be able to retrieve your results. Then, for the same problem, let me modify. Go into this component separator. Be careful when I use this block. I'll be deleting this, or I could start with again a new simulation, but because I'm going to use the same one, so you can say cut. I'll be using the component separator, which is listed under separators. So this is the one. You can read the comment. Component separator separates components based on specified flows or split fractions. So let me take this and put here. See, remember, when you normally have the cursor, when there is no selection made, the cursor will be having a pointer. But the moment I select either a material stream or any model, let me click on this, see the cursor will change to something else, plus. So that means you have selected something. Wherever you want, you will be able to paste it by clicking your left mouse button. And you can also change its size if you want, like this, by dragging the corners. Right? Now, I would like to provide the connectivity. So again, something similar to your splitter. It will have one input stream and you can have any number of outputs. Be careful when I am trying to define this particular block. Generally, this is a very, very simplified block. You will not be addressing what type of unit operation you would be using when you use this model, but you will be able to achieve the required separation by your definition. It is something like pick and place. For example, let me go ahead. Remember, I have already defined S1, which you can see by double clicking this. This came from the previous problem, so it is not asking information for S1. But because there is a change, the required information with respect to this block. Let me press next. Now, remember, this was not the case earlier. We did not have this outlet stream in the case of a splitter. But in the case of a separator, these split fractions can be defined either with respect to S2 or with respect to S3, right? If you, because there are only two outputs. Let us say I am defining with respect to S2. What I mean by this, you try to visualize. We are trying to identify the output stream S2 by giving this kind of a specification. What I am trying to say, when I say 100% of benzene entering into the column should be sent into S2, but it should not allow any toluene. What does that mean? You are able to separate out benzene and toluene relatively into its pure components. Right? Let me run this problem. You can see the stream summary. Of course, again the state is same. Now 100 moles of benzene is entering through stream 1 and all this 100 is entered through stream 2, but no toluene is allowed into stream 2 as per our specification. So what is happening? The 100 moles of benzene and 100 moles of toluene mixture, we were able to have a perfect separation. What was the unit operation by which we will be able to achieve this? Do you think 100% separation is possible by any mass transfer operation? Probably to some extent you will be able to achieve 100% separation through phase change, not by absorption, not by distillation or any other. Right? As you go nearer to that 100% separation, the driving forces become very small, very small or infinite small. So the time required, the size of the equipment will be unmanageable. So you have to be very reasonable while specifying this kind of separations, right? Normally, we will be using this kind of simplified blocks while performing initial mass and energy balances. Maybe after coming to a convergence with respect to mass and energy balances, then you may be able to replace this column with the same specifications by an appropriate unit operation like distillation, absorption, or whatever, right? So don't be unreasonable like this, having 100% separation, which may not be possible by using an appropriate unit operation. So let me once again define, just to show you the difference. Now I will say this, and will say 0.1. Do you think the sum of these split fractions must be 1? Remember, we are not addressing this. It can be, this is valid. What I am only trying to say is, all the benzene entering into the column should go into stream 2, but only 10% of the toluene entering into the column should be allowed to go into S2. So there will be no benzene that goes into S3. 90% of toluene that is entering will go into S3 because you know mass has to be conserved. So let me run this again and look at the stream summary. Now you can see all the benzene is going into stream 2. Out of 100, we said 10% is allowed. 10 moles are sent into stream 2. The remaining 90 moles are going out into the other stream. So this way, you will be able to pick and place whatever amount of separation that you want. Remember, this, even though this is a simplified model, it will be able to perform the mass balance as per definition, as well as energy balance. Now, the energy balance will not change just because the this particular model is replaced by something like a distillation column. Of course, in the case of distillation column, maybe you have other units coming in which will affect the energy balance, but the quantities of energy entering through stream 1 and stream 2, stream 3 will not change, as long as you keep the property method the same, right? This is how the calculations are done in the case of component separator. Now, with this background, I would like to close this session.